All right, so we talked about a couple things there. First, something your book calls the mass defect. That's not just your book, they call it the mass defect. I don't know if you've ever noticed this on the periodic table. Let me pull up a periodic table and show you. Let's see, is this one good enough? Yeah, this will work. So here we have this periodic table, and if you notice, the mass of hydrogen is 1.00794. Now, the mass of helium should be about what times the mass of hydrogen? Do you know? Twice, 3 times, 4 times? What should it be? You'd think, but the mass of hydrogen is actually just 1 proton. So this mass is just 1 proton, but the mass, your helium atom is made up of 2 protons and 2 neutrons. So it should be about 4 times. So we have this 1.00794, and if we multiply that times 4, what do we get? Let's see, somebody tell me that. What's 1.007 times 4? Or 1.008 times 4? 4.03? Okay, 4.028, 4.03. But notice that over here we have 4.003. So we're off by an order of magnitude, or rather that decimal place is off by an order of magnitude. So we actually, a helium atom is a lot lighter than it should be. Well, it's a little bit lighter than it should be. And that's what he was talking about there with the sort of the splash balls, that when they fuse together, that they actually become lighter, that they lose some of their mass, which becomes energy. And your book talks about this in terms of this mass defect. And because we have this expression relating mass and energy, and it's related to the speed of light, you know, the speed of light is 3 times 10 to the 8th. And when you square that, that becomes, 9 times 10 to the 16th. And so any amount of mass is going to create a huge amount of energy. So this tiny little bit of mass, as you go from hydrogen to helium, is going to produce a lot of energy. Let's see, it tells you the amount of energy. Oh gosh, I don't know, maybe it doesn't. I think the sun puts out like so many yotta joules. I don't even know what a yotta is, but it's a lot of energy, okay? They also talk about the strong nuclear force and the weak nuclear force. We sort of mentioned this in class. I don't know if y'all remember when we listed the 4 fundamental forces. We had the gravitational force, we had the electric force, then we had the weak nuclear force, and the strong nuclear force. The weak nuclear force is at play in different like nuclear reactions, but the strong nuclear force helps to hold the nucleus together. And it is by far the strongest of the 4 forces, although it operates only over very small distances. So your atoms have to be, or your particles have to be very, very close in order for that to happen. It only basically happens between protons and neutrons in the nucleus. All right, let's see if there's any questions here. Yeah, let's do number 508 and 509. These are pretty straightforward. Let's try that. 508 and 509 down here in the bottom. We'll do 508 first. All right, I'll stop at 38. 38. Like we're missing somebody. Okay, good. B is the right answer, fusion. We'll talk about these other things, fission, alpha decay, and beta decay. But let's do 509 now. The mass of the sun is most likely doing what? Increasing, decreasing, not changing, or does it go up and down in time? All right, I'll stop at 28. Okay, awesome. B is right. The mass of the sun is decreasing over time. It's losing a certain amount of mass every day, like he talked about. He mentioned that people often think that the sun really is sort of this fire, but it's really not that at all. That the source of the sun's energy doesn't come from the burning of any kind of fuel, because then it would be gone in like no time at all. But it's this fusion that causes the source of the sun. All right? Yeah.
The mass of the sun is decreasing. Does that mean there'll come a day when it gets really, really small?
Gosh, there will come a day actually where it will expand and get bigger, and it'll sort of engulf all the planets, or at least all the inner planets, and because it gets bigger as it goes through this process. I forget exactly what the process is, but as you begin to burn a lot of the hydrogen and turn it into helium, and then you start fusing helium, eventually you're just going to run out of fuel. I mean, we're talking billions of years in the future. I think like another 5 billion years or so, it's supposed to go into this red giant phase where it puffs up really big before it condenses down to like a neutron star. Don't worry, we'll be out of here by then.
That's my calendar. I think we'll be okay.
Right, yeah, I'm pretty sure we'll be fine. Much bigger things to worry about today than that. Okay? All right, let's look at fusion and fission. First of all, let's talk about this isotopic notation. If you're not familiar with this, it's useful to know it. When we give elements, we write them with their atomic number and their mass number. This really just has to do with stuff that's going on inside the nucleus. So let's say that I have an atom. I put a number here and a number here, A and Z. This is our atomic number. It's going to be the smaller of the two numbers. And then this number up here is our mass number. It'll be the bigger of the two numbers. The mass number includes the protons and neutrons. All of the particles that are inside the nucleus. And the atomic number, on the other hand, just corresponds to the number of what? Protons, right? And whenever we look at a reaction, we'll look at a few, but whenever we look at a reaction, we need to conserve these numbers. So if you have a drop in one of these numbers, then you have to have that accounted for in some way. Okay? So the top number, remember, is the bigger number, protons and neutrons. The bottom number is just the atomic number, just the number of protons. They will talk about electrons, but it's not electrons that orbit the nucleus. They're electrons that are either captured from the outer orbitals, or electrons that are emitted from within the nucleus. So they talk about how the neutron is actually made up of a positive and a negative particle, and they call that negative particle an electron. But don't confuse it with the electrons that are orbiting around there. We're really just talking about the nucleus and nothing else. Okay, so fusion we've already talked about. They give the process of fusion on page 311. I'm not going to draw it, but it's very much like he talked about, where you have these two hydrogen elements come together. They emit a positron. Well, I'll draw it. So I have these two hydrogens. They come together so that you have a proton and then you have a neutron, because you emit a positron. Well, I'll let you look at it on the page. And then those combine with other particles that are floating around in this soup, if you will, protons and neutrons, until eventually you get to a helium-4 atom, where you have two protons and two neutrons. It's on page 311. I'll leave that for you. But the idea is that we start with hydrogen and we make ourselves into helium-4, emitting a lot of energy along the way. Fission, on the other hand, so fusion largely just happens in small nuclei, hydrogen mainly, but you can also get helium that will fuse together. You can also get lithium fusion as well in some cases. Fission is larger atoms, larger nuclei, which break apart. And that can happen in a number of different ways. We're going to look at some radioactive decay. But fission is let's see, they give an example of fission where you start with U-235. This is the example that they have on 312. U-235, which has 92 protons, and then 235 minus 92 neutrons. This combines with a neutron. So my neutron, notice my number up here is going to be 1. What's the number on the bottom for a neutron? The number right here for my isotopic notation. It's not going to be 1. Remember, 1, this is our the number of protons and neutrons. I have 1 neutron, but down here, this is the number of what? Protons. And how many protons are in this neutron? 0, right. So when I write the notation for a neutron, I'm going to have 1, 0 for my neutron. And then this gives us U-236. It's going to be U-236 92. So notice that my numbers here are all conserved. They all add up, right? But this is in an excited state. So often we'll write a little asterisk there to say that this thing has more energy than it had before because I've now taken on this neutron and it brought energy to this system. And then it further breaks down into xenon, which is 140, 54, with 54 protons and some 90 odd neutrons, plus strontium, 9438. Excuse me, SR. And so how many neutrons, I'm going to have some neutrons that are produced by this, how many neutrons will I have left over? Well, if I wanted to know this, I would say, well, I know 54 plus 38. That's what, 84 plus 8, 92 protons. And I have 140 plus 94. What's that? 234? Is that right? 234 protons plus neutrons. All right? So if I have 234 protons plus neutrons, I have 92 protons, which is the same as what I had up here. Then how many neutrons am I going to have left over? If I say 234 minus 92, what does that give me? 142. So if I say 234 minus 92, what do you say, 142? That means I have 142 neutrons. But how many neutrons did I have up here? I have 236 minus 92. That is 144 neutrons up here. So how many neutrons will I have here? I'm going to have 2. So you might have to balance some equations like that, but they don't work exactly like they do in chemistry. You're really just looking at the atomic particles, at what's inside the nucleus. Okay? So in that way, I think they're simpler. But all right, let's look at the different kinds of radioactive decay. We had several different kinds. We had alpha decay, beta decay, gamma decay, and electron capture, which is really just the opposite of beta decay. In alpha decay, emit an alpha particle. And an alpha particle has 2 protons and 2 neutrons. So the upper number here is going to be 4. It has 2 protons plus 2 neutrons. It's basically a helium atom, right? 2 protons and 2 neutrons, and so it has these numbers 4 and 2. So when I have alpha decay, that means I lose an alpha particle. So if I have an element X that is A and Z, this is going to go to X, A minus 4, Z minus 2, plus my alpha particle 4 and 2. And then so all my notation balances out. I lost a 4 up here, but I gain it over here. I lost a 2, but I gain it over here. Okay? Is she causing you trouble, Heather? All right. See, that's alpha decay, beta decay. The beta decay, you lose a beta particle. Basically, in beta decay, a proton becomes a neutron. If you lose this positive particle, from your proton emits a positron, which is a positive particle, and it becomes a neutron. So in your atom, your proton becomes a neutron. So if we're starting out with X, some unknown particle, A and Z, what's going to happen to my numbers here? First of all, what's going to happen to A? That is my mass number, right? The big number. What's going to happen to it in beta decay? I'm sorry, what did you say, Ashley? It's going to stay the same, that's right, because my proton isn't actually leaving, it's just becoming a neutron. So it's still going to have the same mass, and so I'm going to have X, A, but Z, remember, is the number of protons. So I am losing a proton. It's like the proton is switching sides. I'm going to have Z minus 1 over here, and then I have to add in my beta particle. All right, so that is our beta particle. All right, we also have gamma decay. Gamma decay doesn't really change the atomic structure of the nucleus at all, but it does change the energy. So in gamma decay, it's like the atom just loses energy. All right, so I have some particle, A, Z, it's in some excited state, and so it loses a gamma particle, or excuse me, a gamma ray, plus some gamma ray. It still keeps the same mass, but it loses this excited state, and it emits this gamma ray, which is just a photon, just a high energy photon. So the nucleus doesn't change structure at all. And then finally we have electron capture. Electron capture, you have this nucleus, and you have these electrons that are moving around. It's like this electron, they reach out and grab it and bring it into the nucleus. And when you do that, what happens to your protons? If you grab an electron and you bring it into the nucleus, what happens to one of your protons? It does what? Okay, but if I put a proton and an electron together, a positive and a negative charge, what's it going to do? It's going to become a what? A neutron. So this is basically just like the exact opposite of beta decay. In beta decay, the neutron, or excuse me, the proton. Wait, no, that's not the opposite, right? Yeah, so it's basically the same as our beta decay. But I'm capturing this electron. So I have X, A, Z. I add in this electron, and I get this new element, which is going to be A, Z minus 1. that's not right, is it? Yeah, that's right. I'm forming a neutron. Is it right? Yeah, I'm forming a neutron. So I have here a proton that is becoming a neutron. Okay? Y'all with me on this? Yeah. Okay. Let's see. I think I had some questions about this. Yeah, let's try this. We'll try that question number 119. Don't worry, we don't have a whole lot left. We'll be wrapping up here pretty soon. Oh yeah, we just have half-life left, so we're almost done. All right, let's try this 119 over here. When this beryllium undergoes radioactive decay by electron capture, the resulting nucleus is what? So what happens in electron capture? What happens to the nucleus? Well, I bring this electron into the nucleus, so what would happen here? No, I'm sorry, number 119, up here in the top. Right here. Let's do 490 after this. So when you're done with this one, go ahead and look at 490, and I'll stop this there in just a second. All right, I'm going to go and stop this. Okay, awesome. B is right. I think that's right. Yeah. So when I have this electron capture, I go to lithium here, the 7,3 lithium. Now let's look at 490. Radon decays to, what's that, polonium, I think? What type of particle is emitted? We're looking at 490. You should be able to look at the mass number pretty quickly and realize what it does there, what kind of particle it emits. After this, we'll do 488. Just want to look at that. All right, 35, I'll stop. B is right. All right, my mass number is going down by 4, so that should key you off right away that I'm looking at an alpha particle, which has a helium atom, a helium nucleus rather. All right, and 488. I'll stop at, say, 32. That's right, D is right. Very good. So in electron capture, a proton and an electron are destroyed, and then they produce a neutron. Or you can think of them as coming together and producing a neutron. That's not exactly what happens, but I capture this electron, and it makes a proton become a neutron. All right, good. All right, we're almost done. Let's look at half-life, and then we'll wrap it up. In a half-life, if you have a half-life of a material, it just means that in that time, that half of the total substance is lost or decays in that time. So like, for example, let's say that we have 500 grams of a material that has a half-life of, I don't know, 10 years. And that means that after 10 years, I have 250 grams. After 20 years, I have how much? 125. So I lose half of my mass each time. After 30 years, after another half-life has passed, I get half of 125, which is what, 63 grams. And then after 40 years and on, each time I lose half of my substance. And so you can think of this in terms of the amount of substance that I lose is a half times, or rather raised to an exponent of n, the number of half-lives, where here n is the number of half-lives. Right, so if I have 3 half-lives, for example, then I'm looking at 1/2 to the third, which is equal to 1/8. So if I have 3 half-lives, then I'm down 1 to 1/8 of my original substance. Okay? And now finally, let's look at exponential decay. They give you the equation that describes exponential decay, this delta n over delta t equals to negative lambda n. This is a differential equation where really it should be written as dn dt equals negative lambda n, and it only has a solution that's based on an exponential. So this is really what you need to be worried about, that the number of nuclei that are not yet that have decayed or that have not yet decayed is equal to n naught times e to the minus lambda n. So this is the solution to this differential equation. This equation right here. It is an exponential. If we look at an exponential, we saw this with RC circuits. An exponential function looks like that. They give you a picture of it. I think when you're working with that, you need to remember that there's something I wanted to tell you. What was it? I don't remember. Let's do some of these quicker questions and we'll wrap it up. Okay, so let's look at number 481 up here. It's a half-life problem. Excuse me. Number 481. Substance X has a half-life of 12 hours. It has 400 grams. How much remains after 2 days? All right, I'll stop at 50. Just a few more seconds. A is right. So on this, you would just say, you can do it a couple different ways, but the easiest way is just say 1/2 to n, where n is the number of half-lives. In 2 days, we have 4 half-lives. 12 hours goes into 1 day twice, so I have 4. So that's 1/2 to the 4th, which is 1/16. And 1/16 of 400 is 25. Or you might just go through it piece by piece and say, well, after 1 half-life, I have 200 grams, and then I have 100 grams, and then I have 50 grams, and then I have 25 grams. Let's look at 483. This one's a little bit different. How much time has passed? If I started with 384, and then I finished with 12 grams. Okay, doing pretty well. I'm going to stop at 50 seconds. B is right. That is right. Good. So a couple different ways you could have done this. You could just go through each piece and say, well, gosh, 384 divided by 2, that's 192. And then 192 divided by 2, that's 96. and just go through each process, and it takes you 5 half-lives to get down to 12. So you get 96 divided by 2 is 48, 48 divided by 2 is 24, 24 divided by 2 is 12. So that gets you to your process, but you have 1, 2, 3, 4, and 5 half-lives ahead to pass. Let's just do one more. Let's do number 12 over here. This one's a little trickier, and then we'll finish with that. Let's just do number 12, and then we'll stop. All right, I'll stop at 55, 55. Oh yeah, we're all over the board here. Okay, yeah, so the slope here is b. It's negative lambda. Look, I'm starting with this function, n equals n naught e to the minus lambda over t. And it's asking, what if I plot the natural log of n over n naught versus t, then what is the slope of that equal to? So I want to put this in the function of y equals mx plus b, and then the coefficient of that x will be our slope. So I have n over n naught equals e to the minus lambda over t. And then if I, lambda t, I'm sorry, not over t, times t. This should be times t. All right, I take the natural log of both sides. The natural log gets rid of that e, and so I get natural log of n over n naught. That's what I have here, equals negative lambda times t. And so this is my y variable, this is my x variable, so this is my slope, negative lambda. Okay, we'll stop there. Listen, next time you're going to do the physics exam, it'll cover this material and waves and sound, especially with the waves and sound. Like I said, we're going to cover that in the class, so it'll be good for you to go ahead and get a little extra head start on that, because it's kind of new material for a lot of you. And then when we come back together on the 29th, which will be our last meeting, we'll do optics, but we'll treat that a lot like a help session for the test, which is coming up that next Monday. The only material we'll cover will be that which is going to be on the test, diffraction, lenses, stuff like that. So that'll be really helpful, I think, for you, hopefully. Y'all hang in there, okay? The MCAT's really daunting, and I know that y'all have tons of other stuff to do, but it's good for you to sort of set aside this time to focus on it. Cumulative? What test?
You have to so this class.
No, just waves and nuclear, the two chapters. Okie dokie. All right, I'll try to write something more appropriate.